So 12.2 is the last unit that we have to talk about. And basically we have to talk about this because I've said it multiple times, we really don't deal with nonlinear data. So I'm back to scatter plots. I'm talking about bivariate sets of data where we talk about soft. So we've got your strength, your outliers, your form, and direction. And we really, really only talk about linear sets of data. So what happens when I have something that's not linear? So in this first example, they're graphing the under 5 mortality rate versus the income per person. So they're looking at the mortality rate to see if they can predict the amount of income per country. So you can see over here on the left, you've got the countries, their mortality rate, and then the income per person. So when you're looking at this data set, you can very clearly see that that is not a linear set of data. So we pretty much have 3 different ways to try to transform it. The first one is we're going to use the reciprocal. So if you look down here, basically what I did, you do not need to necessarily know how to do this, but what I did was I went to a spreadsheet and I took all of this one right here. This one's 1 over the mortality rate. So I took this column right here and I took all of these points and I did 1 over each one of them. And then I graphed 1 over this versus the income. So if you look right here, it's 1 over the mortality versus the income. And then I got, this is the residual and this is the computer printout that I got. So that will be my y-intercept and that will be my slope right there. So if you're looking at this, like, there might be a little bit of a curved pattern, but it's definitely going to be better than what this was up here. So that's not too bad. You can start to look at things. I guess I should have done the regular scatter plot too. But anyways, transformation number 2 is leave this one, and then we're going to do 1 over the income per person, which gets you this computer printout right here. Again, this is going to be your constant or your y-intercept, and there's your slope right there. And I do kind of like this residual plot a little bit better. Now is when you can start analyzing S, which is your standard deviation, which is your typical distance from the prediction line. So you're off by about that many thousand. So about $44,797. And then we're going to talk about over here what that means for that too, because now we need to know how to work with this data. So I just copied and pasted this down here so that we could get some practice with writing the equation of the least squares regression line. So for over here, whenever you're writing these, remember you have to label what your values are, and you need to say predicted, and that needs a label. And then that's going to be equal to the constant plus your slope. And then that will be times an x value. And again, that also needs to be labeled. Now, this one does work slightly different, but let's go ahead and get started. So the first thing that we're going to be talking about is we are going to be predicting the income. So predicted income is equal to, and then you use the constant, which is 869, plus your slope, which is this right here, 104,868. Now, this would be times the reciprocal. So this is going to be 1 over that mortality or the under 5. So that is going to be important that you need to do 1 over that, because then we're going to start to predict. So it says predict the income for a person for Turkey, which had a child mortality rate of 20.3. So then I would say the income would be equal to 869 plus 104,868 times, and not just the mortality rate, but 1 over the mortality rate. And then you plug that in on the calculator and you get that 6,034.91. And that is the predicted amount of income. Okay, so same thing over here for this one. So we have a different equation this time, because this time we're doing 1 over income. So we're going to do the 1 over the income predicted is equal to negative point, that's a lot of zeros, 1, 2, 3, 4, 5 zeros, 5, 8, 5. And then that will be plus your slope, which is the same 1, 2, 3, 4, 5. 829, and then this time it's just times the mortality rate, which is the under 5. And you can look up here to see we just transformed the 1 over income. So if you think about back to that slide we were just talking about over here, so the first one, what I did was I did 1 over the mortality rate, left the income. The second one I did 1 over the income and left the mortality rate. So now we're going to plug in the 20.3, so that'll be equal to negative 0.00000. 5 zeros, 1, 2, 3, 4, 5. 585 plus 0.12345 zeros, 829, and that's times the 20.3. Now plugging that in on the calculator, you are going to get 0.000162437, and that is equal to 1 over the income predicted. Now, as you can see, like that's obviously not the income per person. I mean, that's less than a penny would be the income, where over here we had predicted that it'd be around 6,000. So this is obviously not correct. That's just because it's not done yet. So this is 1 over the income. So if we do 1 over that number, then we can find that the predicted income is going to be 1 over 0.000162437, which will be equal to 6,156.23, and that again will be in dollars. Okay, so you can see their predictions are pretty close. We could talk about the R squared value and the R values, which both of these should have, is it negative? So when you square root them, just to note, to find your R value, you would have a positive, but I believe it'll end up being negative because it's the plus or minus. Okay, so that's using the reciprocal. Now let's use logarithms. This is what we would call a power rule. So when you natural log both sides for this transformation, it's the exact same one as the one above. We transformed both of them, and then we got this scatter plot right here. And this scatter plot is kind of beautiful if you look at it. Like it's got that negative relationship there. You can clearly see that there's a line. There's your residual with that scattered pattern. So if you're comparing that with these two, this is wonderful. So I would say that we're on our way to having a really good transformation of data. So power model, again, that's where you natural log both variables. And the reason why it would be good to use is because, again, look at that residual. You can see that there's that chaos that we're looking for. For part B, it says give the equation of least squares regression line. So for part B, this is just like before. So this time, we're going to be predicting the natural log of income, and again, that is predicted, is equal to my constant 11.4950 minus 0.93740. Oh, I take that back. The other ones had positive slopes, didn't they? Because my slope was positive, so positive R values. This one will have a negative R value. So then that would be times the natural log of that under 5. Okay, so both variables have been transformed by doing natural logs. And again, just like before, we want to figure out what that will be for Turkey. So we have the natural log income predicted is equal to 11.4950 minus 0.3740 times the natural log of 20.3. Okay, so you type that in on your calculator. So if you type just this in, the natural log key is on the left-hand side. It's the second E key. You should get, one moment here, 8.6728. And again, with that, like that does not make sense. So that should lead you to believe that you're just not done with the problem yet. So now you have to figure out how to undo a natural log. So how to undo a natural log is you're actually going to E both sides. So therefore, your income predicted will be equal to E to the 8.6728, which is equal to 5,840 $42. And again, not that far off from the other ones. Okay. And then last but not least, I did not do the same example, but a different one with an exponential model. So this one's an M&M example. You can read through it, but basically here's your graph. So this time I just natural logged the y, the output, and that's what makes this an exponential. So with a reciprocal, you can do 1 over both variables, 1 over one variable, 1 over the other variable, not so picky. With a power model, you log both variables. With an exponential, you just log the y's. So there's that residual plot. So the scatter plot, the residual plot, everything leads me to believe that this is now a linear set of data. So we're going to do the same thing that we did before. We are going to do the natural log remaining predicted is equal to your constant 4.0593 minus 0.68073, and that will be times the course. Okay, so then it says, I don't know if I added anything else to that or not. I think I just gave you an example of what to do if we wanted to figure out after how many courses to predict the original number of M&Ms per bag. We would plug 0 in for X. So if I want to know how many were started, so what would be like the original number, I would still have the natural log remaining predicted would be equal to 4.0593 minus 0.68073 times 0. So that's going to make that be 0. And just like in that last question, when you want to undo a natural log, you E both sides. So we would have the remaining, in this case, the beginning, started would be equal to E to the 4.0593, which would give you approximately 57.93 as your way to transform it. Okay, so that's it. That's everything. So to conclude with this one, we pretty much have 3 transformations that we normally use. I've also seen square roots and squareds, but again, if you have the square root over here, then you're just going to square both sides. You just solve it like a normal equation. Just make sure in the end you just have remaining, not like natural log remaining or 1 over or anything like that. So plug in your variables. Make sure you label all of your variables. Your constant is your y-intercept, and whatever's labeled is your slope. And then we can review other stuff in our review.